Previously, we looked at plane mirrors, and we saw that the image that was produced was pretty simple. It wasn't really anything complicated. The magnification was 1, so essentially the image was, almost exactly like the object. There was a left-right reversal, but the image was also right side up and virtual. Now we're going to look at spherical mirrors. We're going to see what happens when we grind a surface to a mirror with a spherical shape, and some of the possibilities that we have with both a concave type surface and a convex surface. So these are going to be a little bit different. Not only is the image going to have the possibility of being real or virtual for the concave mirror, we're also going to see a different magnification. So let's see what we're looking at when we're looking at a spherical mirror. Now, let me just caution, spherical is not the optimum shape for an optical system. Later on, we'll see that we can actually run into what's called spherical aberration, because the shape doesn't produce a very well-controlled focus. That's putting it mildly. So spherical aberration is a problem for these, but originally these were the easiest types of mirrors to grind. Spherically, you just had to move the surface around a common focus, and you could get a fairly consistent surface. And you tried to grind any more complicated mirrors than this. It was really quite a challenge. Now, today we have computerized grinding machines that can produce parabolic shapes and hyperbolic shapes, but back in the day when these were first being developed, and Sir Isaac Newton developed the first one, there was a challenge to really create anything other than a flat surface or a spherical surface. So again, we can imagine that our spherical mirror is essentially a surface, either convex or concave, such that the surface basically is defined by some part of a sphere. So we can imagine some sphere, radius r, and that in this case, we have a concave mirror. The surface of the sphere represents part of the surface of the mirror. So concave, the old way I always used to remember concave, convex, the concave mirror was caved in. So again, there's going to be some radius r, and this, the radius, of course, is going to determine how much the rays converge or diverge per particular distance. So once again, you can coat the outer surface of a sphere with, I should say spherical surface, can be the outer surface of a spherical surface to become a convex mirror. That would be basically putting the reflective surface here, or on the interior of the sphere, that would be concave. So this is the concave mirror. This is the original mirror that was used by Sir Isaac Newton to create his reflector telescope. And it basically converges the rays when the rays are coming in parallel. So you form an image of anything that is distant, and that would basically come to a point at what we would call the focus. So this is important. All these mirrors, all these lenses are going to have a focus. And the focus is, if the rays came in parallel, this is where they would converge, okay? In this case, this focus is going to be on the real side of the image. In the case of some other optical systems, you might actually get a focus in the virtual part. Basically, the focus is on the negative side, but we'll talk about that when we get to the convex mirror. So here is what a ray will do when it's bouncing off of the surface. Now, what you notice here is we have a ray coming in, and it's basically coming in parallel. This is a ray that would typically come from an object very, very far away. if all the rays are parallel. This is just a single ray, so you can't really say. But the ray, the angle of incidence is going to be equal to the angle of reflection. So when we take a look at this here, theta represents the angle that the ray makes with respect to a line going from the center of curvature to the point X. And that's important there because basically that line from the center of curvature to the surface of the mirror, that point X, is perpendicular. So basically that's the normal, all right? And that means that this angle of reflected beam is going to be equal to that angle of incidence. And again, the ray is finally going to pass this way. And here's the important point. It is going to pass through a point we call the focus, okay? And the focal length is the distance from the surface of the mirror to that focal point. So again, the focus here, this F, represents the point where all parallel rays, all rays essentially coming from objects at infinity, are going to converge to. It doesn't matter where you choose the place that the ray is going to hit. So for instance, let's say I take a ray right here. Now again, the normal, I'll use a solid line here. The normal between the center of curvature and the surface is going to look like this. So finally, the new ray there is going to also converge at F. So that's basically what we have for our concave mirror. F, because of what we just demonstrated here, is 1/2 the distance of the curvature. So if you know the radius of curvature, and let's say the radius of curvature is 20 centimeters, the focal length of that mirror is going to be 10 centimeters. Now again, spherical mirrors are not ideal. They were basically what was able to be created early on when they physically grind these mirrors down. They would take a blank piece of glass, they grind it down and get it to the spherical shape, and then they would polish it. But you know, one thing that you might see is that although I traced very nicely that everything came to F, the reality is, especially when you have a very small radius of curvature, the points at which all the rays, this is a little bit of an exaggeration, but the points at which all the rays converge is not entirely at F. F is actually spread out a little bit, if you will. The proper shape for this mirror to get rid of spherical aberration would be parabolic would reduce it, and hyperbolic would be the ideal. But again, the way that these mirrors were made, it's very difficult to grind it to that particular shape. So again, parabolic mirror, you can notice that all the rays are converging at F over here. A large spherical mirror, okay, or I should say a mirror where the radius of curvature is comparable to the size of the mirror, you can see you're going to get quite a bit of spherical aberration. And of course, in the smaller mirrors, where the radius of curvature is large compared to the mirror, that spherical aberration is usually not as pronounced. So let's go back to our equation for magnification. We define magnification as the ratio of the height of the image to the height of the object. What is interesting is by geometry, we were able to show that the magnification was also proportional of the distance of the object to the distance, the distance of the image to the distance of the object. Now, we are going to include this negative sign right here to indicate that the image is going to be inverted when it's real, okay? That basically the object and the image are going to be on the same side of the mirror, the reflecting side of the mirror, and that when the image is real, it's basically upside down. So here is the case where we've placed an object beyond the radius of curvature, and we can calculate the position of the image. Typically, we don't use the radius of curvature to indicate where the distance of the image is. We oftentimes will replace this with 1 over f, knowing that f is equal to 1/2 of r. But for now, we'll use what we have here. Okay, so let's see how we created this image. We're going to draw a line. Okay, we're going to draw this red ray right here. And if it hits the very center of the mirror on the optical axis, the angle that it comes in is going to be equal to the angle that's reflected. Okay? Now, we form an image where all the rays converge. Now, if I draw another ray, I'm going to draw this green ray. This ray passes through the center of curvature. The center of curvature is the normal to the surface. So this green ray is actually going to be reflected back. And not surprisingly, we get our image located at this position right here. I've exaggerated size. But we actually get a few different pieces of information. Okay. First of all, this image is going to be real. Okay. It is exactly where the light actually travels. Remember, to have a real image, the light has to physically be able to get to that particular point. It's inverted, okay, upside down. Real images off of a mirror are inverted. We'll see the same is true for a lens. And it's smaller, okay? The magnification is less than 1. Well, it's negative anyway because it's inverted. But again, that is based on the position of these different rays. And this equation right here can describe where the position of the image is. Notice that we use reciprocals here. 1 over the image, 1 over the object, 2 over the radius. Okay, so oftentimes we're dealing with fractions when we're determining the positions of these images. This is called the mirror equation, by the way. But again, we almost always replace this with 1 over the focal length, knowing again the focal length is equal to 1/2 the radius. Now, if the object is very far away, we can make the assumption that effectively the distance to the object acts like it's at infinity. Now, obviously the universe has a finite size, but in many optical systems, even if something is 100 meters away, you can pretty much do the approximation that your distance to the object is infinity. If we take the reciprocal of that, we get 1 over infinity is equal to 0. I'm not going to prove that here, but if you take the limits, you'll see that that is the case. And we get 1 over di. Okay, let me just clear that because I ran out of space here. 1 over di plus 1 over do. I'm going to use f. I don't like the radius of curvature. 1 over f. And of course, 1 over do is 0 when the object's very far away. And what we see here is that f is equal to di. Objects that are far away, again, they will focus at the focal point of the concave mirror. Here you can physically see that. We simulate rays coming from infinity in this photo right here. They're basically collimated by a converging lens, a convex lens, but again, clearly, here's the focus. Here's the radius of curvature, which is at twice that distance. And again, parallel rays are going to converge to that point F, the focus. Here's our image once again. We're gonna see how we can construct a ray diagram. Now, once again, you need to know the equation for mirrors and lenses. 1 over dO plus 1 over dI equals 1 over the focal length. But you can actually do this geometrically using a ray diagram. We're going to do that right here. You can actually generate a number of different rays. Sometimes you can get all of the rays. Sometimes you can only get a few of the rays. And basically, let's see if we can go through this. The first ray, we start parallel. So for instance, we're going to start parallel from the top of this image right here, object right here. And as we head to the mirror, we're going to reflect off the mirror and pass through the focal length, okay? The focal point represents where all parallel rays must pass through, okay? So if a parallel ray hits the mirror, it's going to go through F. Now, the second ray reverses that. What if a ray goes through F? Okay, then it's going to bounce off the mirror and then become parallel. And really what's happening is this again is taking place because if you think about this, the normal to the mirror passes through the center of curvature. So being at half that distance, F, that gets your angle of incidence equal to your angle of reflection. So rays 1 and 2 are going to pass through F, either coming or going, either after the reflection or before the reflection. The third ray comes from the fact that a line drawn from the center of curvature C to the surface of the mirror is going to be normal. So therefore, this purple ray, after passing through C, is going to be reflected and go back through C again. Finally, the last ray. Anytime we have a ray that hits the optical axis, and the optical axis, folks, because I'm going to use this term quite a bit, the optical axis is this right here, okay? Every time it passes through every time a ray reflects off the mirror at the optical axis, its angle of incidence will be equal to its angle of reflection. So basically, it's going to leave at the same angle that it came in. All right, and that provides us with 4 different rays. And where the rays converge, they converge at this point Q prime. Q is the original point at the top of the arrow, and that's where our image forms. So this ray diagram is very, very key in locating the image. Again, you can use the equation with the focal length, the distance of the object, the distance of the image. But this gives you a visual idea of how to place the image. The magnification is going to be negative and have a value less than 1. Well, its absolute value is going to be less than 1. It's going to have a reduction in its size. And again, the distance of the image from the mirror is closer than the distance of the object. So again, for spherical mirrors, the mirror equation can be expressed using the focal length. That's the way that I like to do it. This is also going to be used for lenses, so just get used to this equation right here. All right. Also, let's note something. For the concave mirror, F is going to be a positive number, okay? You'll see for the convex mirror, it's just the opposite. DI, the position of the image, if that is positive, it's on the left-hand side of the mirror. If the light's coming in from the left-hand side, it's a real image. If it's negative, it's on the opposite side of the mirror, and the image is going to be virtual. Okay, let's take a look at a few different examples. This is, you know, you have to excuse my drawings. Imagine, first of all, that this represents a mirror, okay, by itself. It's just a separate image. You're looking at it. And if you placed an object in front of this mirror, as you're looking at the mirror, the object would be upside down and it will look a lot smaller, okay? So this is how the mirror would look like. That's my best drawing that I could do. Now, if we follow the rays, this is the same condition that we saw before. The blue ray passed through the focus after being reflected. What did we do next? We did the red ray, okay, which hit the mirror, and then after passing through the focus, then went parallel. So parallel before, parallel after. The purple ray going through the center of curvature, and then the green ray reflecting at the optical axis. Okay? Now, what happens as I bring my object closer? Well, as I bring my object closer, the image gets bigger. Okay, now we can see that the intersection of the rays is moving further back. And as this happens, remember that our magnification, of course, goes by negative DI over DO. So if we can get our image distance larger, the magnification is going to be greater. It's still going to be negative. Okay, it's still upside down. So now I'm going to move a little bit closer. Okay, now I'm going to move at the center of curvature. Okay, at this point here, if you remember, 1 over d0 plus 1 over di is equal to 2 over the radius of curvature, okay? Or in this case, this is going to be 1 over f, all right? So if the two are equal, 1/2 plus 1/2 equals whole. Or in the case where we have 1 plus 1, we get 2. So for this particular situation where I place an object at the center of curvature, I'm going to get a magnification of 1 or -1, technically, because it's upside down. You know what's happening. As I move the object closer, the image distance gets further away. Now we can see our object is sitting between the center of curvature and the focal length. Our image is magnified, it's still upside down, okay? So I look into the mirror and my object is becoming a larger and larger image in that mirror. And the one place that we cannot get an image is if I try to place my object at the focal length. Here's why. Take a look at the rays. First of all, if we take a look at our blue ray, okay? Take a look at our blue ray. Our blue ray has to go through the focus and then become, I'm sorry, go the other way. Comes from the top of the arrow, it's parallel, and then it has to pass through the focus. With the green ray, we start at the top and then we bounce off at the optical axis, okay? So the blue and the green ray, they're never going to converge, all right? course, the purple ray, I don't have another color to represent it with, so I'm going to just use red. The purple ray passes through the center of curvature and then reflects off of that. So the red ray is also going in the same direction. There's no convergence here. The image will never form. In fact, if you do the equations, you'll find out that the image is at infinity. So placing an object at the focal point will give you no image. Now, if you go in front of the focal length, we get an image which is magnified, it's positively magnified, but now it's virtual. Okay, so one thing that we can't do is go through the focal length with our ray after it bounces off the mirror. We're stuck here with only two rays, really. Our first ray starts out parallel, and then we know after it reflects, it's got to go through the focal point. So the way I represent this is I have to trace it back in time on the virtual side of the mirror. Likewise, I'm going to do the same with this ray right here. This ray is coming from the top of the arrow. It goes this way. So they're not converging on this side. These rays will not converge on this side. When you're stuck with that condition, you need to trace backward, and that's how we get our virtual images. Oops, wrong color. And see, you can see they converge at that point right there. Again, I'm pretty much stuck with just two rays. All right, but that's enough to converge to a point. And that's how I get my virtual image, and it's right side up. And here you can see two of those conditions. The first condition is this condition right here. You'll notice that the image is about the same size as the object. Okay, and the second condition, the candle has been pushed in front of the focal length, so it's virtual now and right side up. And just another ray diagram to reinforce what we've been saying already. Again, inverted image, magnified, and real. Now with a convex mirror, the image is always going to be virtual. I know with the concave mirror, we had the real image when we were beyond the focal point, and then we went to a virtual image once we passed the focal point, and no image when we're at the focal point. Convex mirror, unless we have a image projected on the virtual side, we will never get a real image. Don't worry about that. Okay, an object will not produce a real image in this particular case. So, convex mirror, the proper way to talk about the focal length is it's going to be negative. So, perhaps negative 20 centimeters would be a typical focal length for a convex mirror. And of course, if the focal length is negative 20 centimeters, that indicates that it's convex. The radius of curvature is 40 centimeters. So here's where the focal point is for the convex mirror, okay? Here's the reasoning behind it. Remember, if I have parallel lines coming to a mirror, okay, they will pass through the focal point after they're reflected. Well, if the focal point's on this side, the virtual ray would converge right here, but the real reflected ray would be this over here. Okay, same thing here. It reflects, goes this way. All right, so clearly we can see that the focal length here, okay, is on the virtual side of the mirror. It's going to be negative. We're going to get virtual images from an object. And again, same relationship. The radius of curvature is twice the focal length. And essentially it produces a diverging system. Here's an object producing the virtual image. Let's go back to this picture right here. I don't know how easy it is to see this, but you can see this mirror right here heavily distorts what's being reflected, but it also reduces the magnification. Okay, it's upright, it's virtual, but the magnification is less than 1. So by reducing the size of the image, what you're actually doing is you're able to see more things with that mirror. Okay, more things will fit in your field of view for that mirror. And that's typically what we see for this type of mirror. Okay, they're used for security. They're used for improving our field of view, even though they make everything smaller. Again, doing the ray diagram for this, here's our first ray. We start parallel, and then if we trace back in time to the focus, that tells us that this ray is going to go off in this direction. Our ray, again, instead of purple, I've got to use red. Our ray, which heads toward the direction of the center of curvature. Okay, actually, I got to get rid of that. I got to make this dotted. Let's be consistent here. It's simply going to be reflected back to this direction. And then here, our green ray is reflected at the same angle of incidence at the optical axis. We trace that back, and there's our image right there. On the other side of the mirror, it's virtual, okay? Just like our plane mirror. When you looked into the plane mirror, your image was beyond this, okay? But in this case, if you looked into a convex mirror, you would see yourself, but you'd be much smaller. You'd still be right side up, still that left-right reversal. You just look smaller. And that's really the only possibility here, because we can't move the object between F and C. We can't move it beyond C. So, you know, all objects are on the left-hand side of F and C for the convention that I have it drawn here. Okay. So here is, again, the examples of the concave mirror, okay? In this case, our object being beyond the radius of curvature, we have an inverted lower magnification image. And then here's our only possibility for our convex mirror. Virtual, right side up, also reduced magnification. And again, showing, you know, the candle is your object. You can see the reflection. This is neat because you can also see the camera in the background. Convex mirrors are just great for reducing the images, so your field of view is much bigger. We see them in convenience stores, just very inexpensive way of doing security. You can see more of the store. And side view mirrors, you'll see that objects in mirror are closer than they appear. That again is due to the fact that you're shrinking all of your images there. So your field of view, what you can see, and you can see into your blind spot, you can see just much more. I always love the Escher drawings. Here's Escher actually drawing himself using a convex surface. and then using this reflective jar to draw this. Just a master of knowing his geometry for reflective surfaces. So getting used to the sign convention, all right? For mirrors, DO, okay, it's going to be positive when it's in front of the mirror. If our object is produced by an image, what I'm saying here, if our object is actually an image produced by another optical system, if it's behind the mirror, it becomes negative for DO. But again, we'll talk more about this when we're talking about compound lens systems and telescopes and microscopes. Image location, same thing. If it's in front of the reflective surface and it's real, positive DI. It's behind the reflective surface and virtual, negative. Concave, positive focal length. Convex, negative focal length. Okay. And upright image, positive for H, and negative for inverted. Same thing with magnification. Upright is positive, negative, it's inverted. And by the way, this is from a different textbook, so this should be height of image if we want to be consistent with the OpenStax. So really, two different ways that we can locate an image. I love the visual aspect of ray diagrams. We can just see where everything is. Again, ray diagrams are actually an approximation. But again, to make a ray diagram, you need to know the position of the object and either the position of the center of curvature or the focal point for that particular mirror. You can do up to 4 rays, but typically 3 rays are usually available. And the intersection of any 2 rays, as long as you have 2 rays, you can locate the image. It's the intersection of these where they converge that we have our image. And again, with concave mirror, you saw that we can have a real image, which is inverted. And you can also have, if you go in front of the focal point, you can have a virtual right side up image. Convex mirror, you don't really have a choice. In a single mirror system, the image is always going to be virtual. It's always going to be upright. I said earlier that Sir Isaac Newton was the first to invent the mirror telescope, the reflector telescope. And it's really amazing that we're still using his basic optical system today. Now, of course, his telescopes were inferior to the telescopes we have today. The primary mirror was spherical. The secondary mirror created a fairly large obstruction. What's amazing is you put a mirror in the path of some of these rays, it doesn't create a big dark spot at the center of the image. What it does do is it reduces the contrast of the image, okay? The image is not as crisp as it would be if that obstruction wasn't there. The Newtonian reflector sends the image off axis, okay? Whereas some more modern reflectors like the Schmidt-Cassegrain will actually send the light through a hole in the primary mirror. But again, that was the Newtonian reflector, which is the basis for all the famous telescopes that you know of, the research telescopes. Hubble, famously, they ground the mirror, so it was the wrong shape. Believe it was not a spherical mirror, but it wasn't the proper parabolic shape. it was somewhere between spherical and parabolic, but I'll have to revisit that to know that. They had a computer controlled grinding system that basically made the wrong shape, but they went back and they gave it eyeglasses. They actually installed lenses in front of the detectors that would correct for this problem, just like you would if you had an astigmatism in your eye. CAC telescopes are some of the largest telescopes in the world, 10 meters across. There is a larger telescope in the Canary Islands, and they are in the process of building even larger telescopes than this. These telescopes are getting so big that they actually have to break the primary mirror into individual hexagonal segments. And we see this technology again used in the largest of the space telescopes, the Webb Space Telescope. And the Webb Space Telescope is interesting in that it's not really designed to look at visible light. It can look at visible light, can go up to orange light at 600 nanometers, but it's really not designed to operate in the visible. It's designed to operate in the infrared because the space telescope is trying to see through molecular clouds of gas and dust. It's trying to see very high red-shifted objects at the edge of our universe, where what was originally ultraviolet and visible light is now in the infrared. So it can see all the way to 28.3 microns. Okay, just to give you an idea, visible light is about half a micron. 600 nanometers is 0.6 microns. And the reason why it's limited in the visible is because they coat the mirrors with gold. Okay, not because they wanted to make this really expensive. It ended up being very expensive. They coat it with gold because gold is a better reflector in the infrared than the typical materials that they'd use, such as aluminum, to coat the mirrors. Also, they don't use glass, they use beryllium. Beryllium is light, it has good thermal expansion properties. So between the beryllium, the gold plating, yes, these were expensive components, but really the expense came from developing all these new technologies to get the mirror to unfold. They fold it up to put it in a fairing, in a rocket. It then unfolds in space. And this thin solar shield or shade allows the telescope to operate, fairly close to absolute zero. So those are mirrors. And again, the concave mirror is the most important, obviously, because we see it used in important research telescopes. Convex mirror. I'm going to confuse those words all the time. Convex mirrors, good for expanding your field of view, good for basically eliminating blind spots in cars with the side view mirror, good for seeing an entire area much better because it reduces the magnification. It has a reduced magnification, allowing the field of view to also be reduced to the size that we can see in the mirror.